Welcome to our next video. So in this video, we're going to talk about different types of experiments. So in the previous video, we kind of introduced the idea of an experiment and we talked about some components of an experiment. And in this video, we're going to talk about different experimental design choices that we have and just a little bit about kind of the reasons why we might choose one particular experimental design over another, some of the affordances of each design. Oops, wrong way there. Okay. So we're going to kind of divide experimental designs into two groups. We have between group designs, which implies that we have two or more groups being compared. And then we're going to have within group designs, where we're talking about taking multiple measures from the same individuals in the experiment. So among between group designs, probably the most well-trusted option would be a randomized control trial, or you might also just hear it called a randomized controlled experiment. And that would be when we're using random assignment to identify different groups that we have and sort those groups. So we're going to have at least two, if not more groups. There's going to be at least one treatment group, and there's probably going to be a control group. That control group might just be the standard treatment, like, something that we already understand and know how it works. It could be a placebo group. It could be a group that has no intervention at all, but something kind of for comparison. And so random assignment is going to be involved in a randomized control trial. So random assignment is where we leave sorting up to random chance, meaning that, let's say I have 100 participants, then I'm going to use like a coin flip to decide who's going to what group. So like person one, if it's heads, I would put them in group A, and if it's tails, I'm going to put them in group B, and I'm going to continue doing that until I get to 50 people, and then whoever else I have left is going to go to the other group. And that would be leaving assignment purely up to random chance. I don't have to actually use a physical coin. I could also just use a computer. I could use a random number generator online or through software to kind of randomly assign one or two or 1, 2, 3 or however many groups to each of my participants in a list, and that would just leave it up to chance. In addition to pure random assignment, you might also see randomized control trials that do some measure of blocking. Sometimes we might actually just call it a different design. We might actually call it a randomized block design, depending on to what level, how detailed we got in our blocking. But blocking just means that ahead of time, we're recognizing that there might be some important subgroups that we want to make sure that we're dividing equally. So that might be because, number one, we don't have a whole lot of people in our study, and maybe we don't trust pure random assignment. If I only have 40 or 50 or 60 people, maybe it's a little bit iffy with random assignment that I'm going to get relatively equal groups. So maybe what I want to do is block by gender, block by age, block by race, block by medical history, smoking status, different things like that, to make sure that I'm getting an equal number of people from those subgroups in each of my experimental groups. So it just kind of is like a safeguard for getting equivalent groups, especially if I don't have a whole lot of people in my study. So the way that random assignment with blocking would work is that I would kind of identify a block, let's say smoking status, where I have smokers and non-smokers. So then what I'm going to do is I'm going to randomly assign the smokers to groups equally, and then I'm going to randomly assign the non-smokers to groups equally so that I get the same number of smokers in each group and the same number of non-smokers in each group. But I'm still using random assignment in that process, right? So I'm not just like, okay, well, I'm just gonna make some choices, but rather I'm still leaving it up to a chance process within those subgroups, how they get divided there. So blocking, again, like I said, is a good practice if I have relatively small groups, or if I have, maybe a kind of the sub-characteristic of interest that I know has an effect, or that I do want to study for a possible effect. And so it's just good to make sure that I have equal numbers in each group for that comparison later. But you always want to be careful with blocking because Blocking for the most part is going to be a good thing, but just remember that whenever humans are involved in decisions, the more we can leave up to random chance, usually the better. The more human bias, or the more human decision gets thrown into a process, the more chance for bias can creep in, even if it's subconscious. So you don't want to kind of mandate too much control, like human control over the sorting, if you can kind of, do away with it. The more you can kind of trust random assignment, I would say generally the better in design. We also have a matched pairs design, and this would be if what I have is two people who are matched together but assigned to different groups. This is a really common design that you would see if we're doing like an identical twin study. So, for example, maybe I have two people who share kind of the same genetic code, or whatever it is that makes identical twins very similar. Then if I have like 50 sets of identical twins, then I can randomly pick one to be in the treatment group and one to be in the control group, and then I can kind of match their measurements afterwards to see if there's a difference. So it's kind of a slightly more efficient design in terms of the results that I get and what I do with it, which we would talk about in a later chapter when we get to more statistical analysis. But it's just kind of a design to keep in mind that if I have either identical twins or I have some other natural matching units where I can collect two of them, and these should be very, very similar units except for the intervention that I'm applying, then it might be worth doing a matched pairs design. And then we also have just kind of non-randomized designs. So if I'm not using random assignment and I don't have some kind of matched pairs situation, then I'm probably just going to label it a non-randomized experiment. And it can still be an experiment, right? So I can still have an intervention that I have control over, that I can assign units to. However, if I don't use a random process, there's an inherent weakness to my design. So for example, let's say that I let people kind of self-select into the group. Let's just say I said okay, well, we have two groups. Which of these two things would you rather do? Well, I'm greatly compromising my design in that case, because people might self-select into a group because of many reasons, and I might end up with kind of unequal groups. Where the people in this group look different than the people in this group. And now I don't have an apples to apples comparison anymore, where I'm just comparing the treatment versus control experimental setting. Now I'm actually looking at this group of people versus that group of people who are very different. So you always want to be very wary of non-randomized designs and how people got sorted, and whether that's going to create an inequality in terms of this balance between the groups and who's in it. So in addition to these between group designs, we also have within group designs, and there's two that we're going to talk about here. A PrePost design is the simple one, and that's when we just have one group who we have measurements from before an intervention, and then we have an intervention, and then we have post measures, and we're going to compare the pre and post measures to see if there's a difference. So there can be some situations where this is nice. I mean, honestly, we collect data like this all the time if you think about it. For example, if I had a survey on the first day and then I gave that same survey again on the last day, I'm kind of giving a pre-post design here where I'm looking for differences as a result of being in the class this semester. You see that a lot in doctor's offices. I actually remember when I went to a physical therapist, I remember filling out a form right before my first appointment where I identified my pain and the level of pain and my abilities for different things. And then I remember after my last visit, I filled out the exact same form again. So that's kind of a form of a pre-post measure to see if there's been progress. However, as we're going to talk about with internal validity, there are some weaknesses to this design because it's not always clear if it's the intervention itself, like the treatment factor, that's causing any differences versus just other things that might be happening. Maybe in addition to seeing a physical therapist, maybe I've changed my diet. Maybe I psychologically am convincing myself that I'm getting better because I'm seeing a physical therapist. Maybe I'm doing additional stretches or things I'm just learning, online or something at home as well. So it's kind of hard to identify causal links from PrePost Designs. Like they have some threats we kind of have to figure out. Still, it is an experiment. There is an intervention that we have control over. But if you don't have a control group, if you don't have another group of people contributing pre-post measures or something like that, who can also kind of compare their measurements, then there's going to be some questions there about how confident we are in the causal link and the effect being produced. So a crossover design is considered kind of a stronger within group design. And that is when we have people kind of do both things. In other words, we have a control intervention and a treatment intervention. And so basically we randomly assign or something like that our people to either start with the control or start with the treatment. Then we take a measure and then we switch them around, and then they do the other intervention that they didn't do the first time. And so that way we have these, these kind of pre-post measures, but I have pre-post measures from both orders and from both groups. And so that kind of lends itself to some more options there in terms of what I can do. One concern, though, for a crossover design, this is kind of a weakness here, is a lingering effect. In other words, let's say that I'm taking a medication or a treatment for this treatment intervention, and then I switch over to the control intervention, but maybe the treatment intervention's still kind of lingering in my system, maybe because I've experienced before, maybe the medication is still in my system, or maybe it's changed the way I think, right? So there's certain things that can kind of confound that comparison a little bit, where it's not just a clear, like, A, B, there's no crossover in terms of my experience. So you always want to be a little bit careful about that and whether there's a lingering effect that we should consider before using a design like that. But you do see these designs a lot in drug trials and other kind of medical interventions with the idea of ethics involved. So the idea that everybody is eventually going to have the treatment factor. So if you were to study clinical trials a lot more, you'd see this design used a lot and how they kind of put some safeguards in there to try to, be sure that there is no lingering effect based on gap time and things like that. But yeah, this is a very common design that you see in some drug trials and clinical trials. All right, so let's take a look at some different design descriptions, and we're going to decide what type of experimental design is being used in each of these examples. So here we have kind of this general prompt, and that is that we have 100 people, or actually I'm getting ahead of myself here. Researchers are studying the use of a new medication, a tablet taken by mouth once a day, that is designed to lessen the severity and frequency of migraines for people who suffer from migraines. The recruiters gather 200 participants and decide to have 100 participants try the new medication and 100 people take a placebo pill. Which of the following sorting methods do you think will make the most effective comparison, and what type of design do they correspond with? Okay, so our first option is that we could have the first 100 people who respond to being in the study be the control group, and have the last 100 responders be the treatment group. Okay, so we are splitting people into two groups. The way that we're sorting them is that the first 100 people who sign up are the treatment group. I'm sorry, the control group. The second 100 people who sign up are the treatment group. So if you think back, which of these designs is being described with this sorting method? So I'll go ahead and answer since this is a video. This would be a non-randomized experiment, a non-randomized controlled experiment. And that's because this is not a random sorting method. You might be tempted to think it is, right? Because you're just thinking, oh, well, you might think we're kind of leaving it up to chance, right? Because I'm letting it just be up to who signs up when. But there's an inherent bias in that plan, right? Because the people who sign up first might be systematically different than the people who sign up second. That would not be randomly sorting. That would be non-randomly sorting, because that is not an unbiased sorting method. So that's going to be a possible issue. Maybe we'll be lucky and maybe they are equivalent groups. But chances are there's going to be something systematically different about people who sign up first versus people who sign up later. I'm just going to make a note here. This is not a random sorting method. All right, let's look at the next one here. Have the researchers randomly assign half to take the placebo pill and half to take the new medication for 3 weeks. Then everyone completes a survey on how their migraines are going. Then everyone switches interventions for another 3 weeks and answers the survey again. Okay, so this definitely sounds like a crossover design, because notice how we are starting off, like we are randomly assigning people to one group or the other, but then we have the additional element of the crossover. So we're getting kind of another set of measurements. So now we have the advantage of being able to compare people's measurements from both interventions, and also having kind of both layers there. We have some people who did treatment first, some people who did control first, that can be used for analysis as well. But yeah, this would be a crossover design, definitely. All right, use coin flips and sort each person to a group. Heads would be the treatment group, and tails would be the control group. Continue until one group reaches 100, and the remaining people take the remaining slots of the other group. So I actually mentioned this before. This was one way I mentioned how you could randomly assign, but this is random assignment, which would make this a randomized controlled experiment / randomized control trial. And that's because a coin flip is a random chance process, right? So that's not a biased process. It's not like the sorting the first 100 people who sign up to one group, because that has a systematic bias. A coin flip, though, is going to be independent of the person it's being used on. So therefore, I should end up with a pretty randomly sorted and balanced groups of people in this case. You might be a little bit curious, though, at the end where it says, what about the fact that if we get 50 heads or 100 heads before we get to 99 tails, is that a problem? And the answer is no, because it's still a random process. It's still a random sorting process, right? Because they're equally as likely to go to one group as the other. If you think about from the time that I began this process, I don't know what's going to happen. So there isn't a systematic bias built in, and everyone still has a 50% chance of going to each group in this case. So it's really not actually a bias there. The next option is that we can consult demographic information about each participant. So we have age, sex, severity of migraines, and randomly assign each subgroup to ensure proportional representation in each experimental condition. So this is, we'll call it a randomized controlled trial with blocking. So in other words, we're taking kind of this extra step, maybe because we think that these things might correlate with migraine severity, or they might interact with how effective the drug is, or something like that. So, we can be kind of extra safe and just make sure that these subgroups get divided equally. Because if I just do pure random assignment, I'm not going to get exactly equal male and female. I'm not going to get exactly proportional equal age in each group and such. So this is kind of a safeguard there if I just want to ensure that. And so that would probably improve the design. Random assignment should still be fine, but this is just kind of like an extra step that it safeguards that balance a little bit more. Definitely a good idea when I don't have super large groups. I think 200 is a pretty large group, so I don't think it's a big deal. But certainly if I have smaller groups, I would definitely consider blocking more. All right, the last option here is have all 200 people answer a questionnaire to assess the severity and frequency of their migraines, then take the medication, then take the questionnaire again. This is definitely a pre-post design, right? So everyone's taking a pre-measurement, everyone's doing the intervention, everyone's taking the post measurement, and then we're just comparing. So that is definitely a pre-post design. All right, so we'll stop there.